So the second of our rules is called the product rule. And as the name implies, it's when we have the product of two functions. And as opposed to the chain rule where we might have a composite function in reality, so our chain rule typically might have something like the cos of x squared plus 2x plus 1 or something. So we've sort of got two distinct functions, but they're a composite of them. Our product rule is when we have two separate functions. And so I think the easiest way to remember is if we have two different instances of x, that's a really good sign, is that we have two distinct functions, and hence we use our product rule. So our product rule is saying if we have two functions u and v, so say that was u, and that function there was v, well then my derivative is the product of the first, or if you like, it's the first function u times the derivative of the second, plus the second function v times the derivative of the first. Okay, that's pretty much what this notation here says, u times v dashed plus v times u dashed. All right. So let's have a practical application of it, and I think setting up is the best thing to do it. So let's just put with u equal to 2x minus 1. Now there's no doubt we could multiply that root x through the bracket. Okay, absolutely we could, but we can't always do that. All right. So if u is equal to 2x minus 1, u dashed, well the derivative of 2x minus 1 is 2. If I put v equal to the second function, which is x to the half, well then v dashed is 1/2 x to the minus a half. So now my derivative, f dashed of x, is equal to, so I always tend to go the derivative of the first, 2 times the second function, which is x to the half, plus the derivative of the second function, minus a half, times the first function, which is 2x minus 1. And then from there, well, that's our derivative. So from there, we can just multiply through perhaps. So 2x to the half plus, I don't know if we gain a lot necessarily from 1/2 x to the minus a half times 2x minus 1. That would typically be fine. If I wanted to try and factorize that, I might look to bring the lowest term out the front, so x to the minus a half. Yeah. So if I take, we might take the half x to the minus a half out the front. A half x to the minus a half out the front. What does that mean? So my first term, well, don't forget I've got to multiply this term into there and end up with 2x to the half. So what do I need to do? Well, a half times 4 would give me 2. So I end up with a 4. And x to the minus a half times x to the 1 will give me x to the half. Don't forget we add our powers. So that's the reason why we take that lowest fractional base out, because now I've got 4x, and my second term, well, I've taken a half x to the minus a half out, and that leaves me with 2x minus 1. So when we have our product rule, often we get 6x minus 1. Often there's some simplification there that can take place, but unless you're told to leave it in a specific form, well, there's nothing wrong with the previous line that I had. All right, so there's our derivative. Let's move on. So again, you can sort of see how we've got two distinct functions. I've got an x cubed function and I've got a sine 3x function, two distinct places where the function variable x is. So u equal x cubed, u dashed is equal to 3x squared. If v is equal to sine 3x, well then u v dashed is derivative of sine is cos, so and the 3 comes out the front. Okay, and now g dashed of x, use my g dashed of x is equal to derivative of the first, which is 3x squared, times the second function, plus derivative of the second function times the first function. And again, we've got an x squared term that could come out as a factor with a 3. So we might write it as 3x squared out the front of sine 3x plus 3 plus x cos 3x. Okay, and then if we have to evaluate values at a particular point, we can substitute them in, that sort of thing. All right, finally, find f dash of x if f of x is equal to, and hence the equation of the tangent. So, well, we've been given a bit of instruction. We have to find f dash of x first. So if u is equal to e to the 2x, u dashed is equal to 2e to the 2x. Again, two distinct functions. V is equal to x plus 1, v dashed is equal to 1. So we've got f dashed of x is equal to derivative of the first times the second, put brackets around, plus derivative of the second, which is just 1, times the first. Again, we might take e to the 2x out the front. And that gives me what? That gives me, I'll multiply the 2 in. That gives me 2x plus 2 plus the 1 left over, which is equal to e to the 2x times 2x plus 3. So there's my derivative. Okay, so that's the first part. Now find the equation of the tangent at the point 0, 1. So at x equal to 0, dy dx is equal to e to the 0 times 0 plus 3. E to the 0 is 1, which is 3. So therefore, the gradient of the tangent is equal to 3. So y equals 3x plus c. Substitute the point 0, 1 in because that was the point that we were given. So 1 is equal to 3 times 0 plus c. So c is equal to 1. Therefore, the equation of the tangent line is equal to 3x plus 1. Okay, so the applications are exactly what we've been doing in the past. We might need to find a normal line, a tangent line, a maximum or a minimum, which means we need a derivative. Anything to do with the gradient of the function means we need to find a derivative. So what we're looking at now is obviously just different ways in which we can find the derivative.